All right, welcome to section 13.6 on directional derivatives and the gradient vector. So we'll start by looking at directional derivatives, and here you can see we have a surface whose equation is z equals f of xy, and let's imagine you're standing on this surface. Think about it as like a hillside. And if you recall, when we defined partial derivatives, we said that if I were to walk along my surface in the positive x direction, then the slope of our hillside, by definition, is the partial derivative of our function f with respect to x. And then likewise, if I walk in the positive y direction, right, the slope of our hillside there would be the partial derivative of f with respect to y. Now, of course, you don't have to necessarily walk in just one of those two directions, right? There's really an infinite number of different directions you could choose from. And so the idea of a directional derivative is simply saying that if I were to just choose an arbitrary direction, how could I find the slope of our hillside in that direction? Okay, so here, to add a little bit to this picture, let's imagine I'm going to say choose this direction U here, okay, in purple. And put another way, right, I'm going to walk along our surface and stay directly above this line here in green, and I'll call that line L, okay? So if I'm going to walk in this direction and I want to measure the slope of my hillside in that direction, what I ultimately am trying to do is measure the slope of this orange tangent, right? And we're going to give this slope a special name, okay? We're going to call it the directional derivative of our function f at the point P with coordinates a, b in the direction u, okay? And the notation there is capital D, D for derivative, and then this vector u is acting as a subscript, and then we have f evaluated at a, b, okay? So let's go ahead and now set up some things to help us compute this orange tangent slope. So here, just for our reference, I have a bird's eye view looking down on the xy plane, and I can see here's my line L, and there's my point P with coordinates a, b, and then there's that direction vector u, right? And again, I'm just taking this portion of our graph in the xy plane and putting it over here for reference. Now, one thing that I'll come back to here, this direction vector u, okay, and I'll call the components u1 and u2, but here we're going to make, for the moment, just the assumption that this thing is a unit vector, okay? I'll say more why this is an important criteria, but for now it'll just be an assumption. Okay, the other thing I'm labeling here is this scaled vector hu. So if I'm going to measure the slope of a tangent line, I want to take an infinitesimal step in the u direction. And so I'm going to call that step size h, and you want to think about this thing as something really small, like think about it as like a trillionth or something, right? So I'm going to take just a little step in the u direction, and then we're going to see what happens to our altitude as we move, okay? So now let's look at this cross section. What we have here for the horizontal axis is just that line L right there. And then up above, right, you can see the cross section of our surface in green here, right? And so this vertical axis in this cross section is just the z altitude, okay? And here we are at the point, and you're going to start moving in the u direction, and you're going to measure the slope of this orange tangent, okay? In order to do that, well, we're just going to do the usual thing. We'll go ahead and just select a neighboring point on our green curve, okay? And I'm going to go ahead and say that the step size, so moving, right, a certain number of units in the positive u direction now, and I'm calling that step size h, right? That's just what I was saying up here. And so what would the coordinates of this point here along L equal? Well, if I'm starting at the point P, whose coordinates are a, b, and I'm moving along I'm moving along u, right, then my x coordinate for where I end up would be A, my starting x-coordinate, and then I'm going to add this scalar multiple, so in other words the hu1 of the x component of my vector u, right? So this would be where I'd wind up, and then I'm going to have b plus hu2, that would be where I'd end up for the y-coordinate, okay? So now what I'd like to do is measure the change in my altitude as I go from the point directly above P to this new point, okay? So first off, my initial altitude would just be f of AB, and then this altitude right here, that's going to be f of, well, these coordinates here, right? So that's going to be f of A plus hu1 b plus hu2. Okay, and then of course the step size, the run here in the slope calculation is going to just be h. So what we're going to do now is just compute that difference quotient. So this is going to be f of A plus hu1 comma b plus hu2 minus f of AB. So this numerator is just the change in my altitude, and I'm going to divide that by the step size, which is h. And this right here is going to tell me the slope of the secant line that passes through these 2 points. So then to get the orange tangent slope, we of course would just take the limit of this secant slope as we let h approach 0. Okay, so this right here would be our difference quotient definition for this directional derivative. Okay, and as you can probably suspect, this thing would be a really, really big pain to actually compute with directly. Okay, so we're actually not going to use this definition to actually compute these directional derivatives. We actually are going to turn to something a little different that will actually wind up being a heck of a lot easier. So the idea to do this using our line L, okay, to start, right, we're moving along the line L, and what I'm going to do is I'm going to write this in parametric form, okay? So all points x, y that are along the line L are going to be of what kind of form? Well, the initial x-coordinate is just A, and then as I move along L, right, I'm really just adding scalar multiples of the vector u to this initial location at P. So in other words, right, I'm going to be adding various multiples, and I'm going to call these multiples just t. Think about t as like time or just a more generic parameter, and that is multiplying the x component of the vector u, okay? And then likewise for y, this is just going to be the initial y plus, right, the various multiples of the y component of the vector u. Okay, so now what we can do, right, and this is just expressing all points x, y along the line L, and now what I can do is think about how my altitude z varies along this cross section. Okay, so in other words, we're going to restrict z to all points that lie directly above this line. So z would depend on x and y, but since we're just restricting x and y to the line L, right, they then in turn depend on this parameter t. And so we really have a chain rule problem, right? So I can compute the derivative of z with respect to t using the chain rule. So let's do that up here. So I'll say that dz dt is what? Well, the first thing to really emphasize is that dz dt is just going to measure our change in altitude with respect to this parameter t. Okay, so in other words, it will measure the slope of this orange tangent, right? So in fact, that derivative, dz dt, is simply this thing we're calling the directional derivative of our function f evaluated at a, b. But I can go ahead and apply the chain rule to compute dz dt, right? This is going to be partial z partial x dx dt plus partial z partial y dy dt. All right. And now I can say a little bit more here, right? What's del z del x? Well, since z is f of x, y, and we're interested in this particular point P, whose coordinates are a, b, okay, this partial derivative is really just the partial derivative of f with respect to x, evaluated at the point a, b, times dx dt. And see, here's x as we move along the line L. And if I differentiate x with respect to t, that's really just going to give me this scalar u1. In other words, it's just going to give me the x component of the vector u. So I'm going to multiply this by u1, and then plus, likewise, del z del y, well, that would be del f del y evaluated at our point AB. And then dy dt is just going to be what? Well, differentiating here with respect to t, I would just get u2. Okay? And that's all fine and good. The benefit of this expression is that if I know, right, the formula for the function f, then I can compute its partial derivatives, evaluate them at our point AB, and then just form this combination here with the components of our direction vector u. And we will know these in various problems that we're given, right? So this really could be it, except we can take this and rewrite it in a slightly more, in some regards, versatile form. The idea here is to observe that this thing really can be thought of as the result of a certain dot product. Okay, I have something times something plus something else times something else. Okay, so what I'm going to do is I'm just going to introduce this vector whose components are the values of our partial derivative of x evaluated at a, b. That's the x component here, and then the partial f partial y evaluated at a, b. I'm just going to introduce this vector and see if I dot that vector with the vector whose components are u1 and u2. Just recalling how dot products work, this says, right, take the x component of the first vector and multiply it with the x component of the second vector. Oh, that's that product. And then add to that the result of taking this y component of the first vector and the y component here, right? And there's that product right there. So this dot product is in fact equal to this expression up above. And we're now going to go ahead and give this thing whose components, this vector whose components are these partial derivatives, we're going to give it a special name. We're going to call it the gradient, and it has this notation. It's an upside down triangle. This is a capital del, by the way. I'll make a little note here. So this is capital del. Remember the script d, that was the lowercase del. So we're going to call this capital del of f evaluated at a, b. This is what we're going to call the gradient vector. And then we're doing what with it? We're dotting that with this thing. And what is that vector there? Well, this thing is just the vector u, right? That's our direction vector. Okay, so in other words, wrapping all this up, the directional derivative can be computed as the dot product of this new vector we're defining as the gradient of the function f and our direction vector u. Okay, and we're going to see in the next couple of videos that there's some really powerful consequences of computing things in this way. All right, so now the last thing I want to do, I want to go ahead and just formally define what we mean by the gradient of a function f. Okay, so the gradient of a function f of two variables, we write this as this upside down triangle. It's this capital Del, okay, and evaluated at any point, say x, y. This is defined to be simply the partial derivative of f with respect to x at xy, comma, partial f partial y evaluated at xy. Okay, so we're building this new vector here whose components are the partial derivatives of our function f. And as we said in the last page there, okay, the key takeaway for right now is that the directional derivative, right, can be computed as this dot product. We're going to simply find this gradient vector, evaluate it at the point, and then take its dot product with the unit vector that we want to move in. All right, well, we will see this in action in the next video.